Cool. Let's see if that works. So any questions from this? I tried to help you a bit. There's a lot of different ways to do this. You figure out the period. And the phase shift will tell you kind of like where you have to start. You normally start at 0, so the phase shift tells you where you should start. So like on this example, the phase shift was 1/2. So I normally start at 0, now I'm starting at 1/2. The period is 1, so I know I should fit a cycle from 1/2 to 3/2. Because that's one away. A cycle should fit in there. Okay. So what's it mean for a trig function to have a period? What does the period mean? Why does a tangent have a period of pi? Why do we call it the period is pi? Why do we say that? What does that mean about tangents? Yeah, the length it needs, or I can think about it as time too, but how much it needs to be able to complete a whole cycle. So tangent completes its cycle in pi, and then the next pi length will be another tangent, and so forth. Sine and cosine complete their cycle in 2 pi. So 0 to 2 pi, there'd be sine, and then every little interval of 2 pi, there's another whole sine cycle. You with me? The cycle doesn't have to start at 0. It can start anywhere, but that's just the convention. Start it here, and then I can move that piece around. Okay, maybe. All of this hinges on, I don't even know if you guys have gotten into that section yet. If you haven't, I can't help you with your problems because you haven't got the problems yet. So you have to get in there, and I'm hoping once you get in there, this might be a nice little quick reference about what you want to find. There are different ways to do these. If you figure out a different way and you like it better than this, I love it. Of course, that way can't be just graph it and look at it in the calculator. It's not an option. Okay, cool. All right. Is there anyone here that doesn't make any sense compared to what we were doing before with this stuff? Yeah.
Right where it says phase shift, you took out a couple 2 pi, or a pi. How did you get x minus 1?
Yeah, so when I have this here, I definitely want to take a 2 pi out of there, right? So I can see what's happening to the x.
Oh, so it's 2 pi, not just pi.
Yeah. And then really what you can do is, you can do that. Take a 2 pi out, that must mean that was divided by 2 pi, and then that, of course, reduces to 1/2. So you can always do that if you have something freaky coming out. You can just put it underneath whatever's in there. Yeah?
I'm sorry, can I get an extra question?
Yeah.
Forgot
You want to?
get one. Oh, I forgot, it's cordial.
Oh.
I forgot to get it. It already started.
All right. So are there any other, I think somebody had, at least one person had homework questions. Yes?
Yes, number 64 on 6.3.
This is page 460. So it's 30 centimeters, and they want to bend up 1/3 of it. So they're going to show you. So of course that'll be 10, 10. So my scale will walk over. 10 centimeters at an angle. They don't tell us. So there's my theta. Okay, so it kind of makes sense. So it starts off flat, then I bend up these sides by an angle of theta. So that's why the theta is right there. It's just bend that up and bend that up by the same amount. So now I've got a nice little gutter. This is a cross section of it. Blah, blah, blah. Show that the cross-sectional area of the gutter, so this area here, cool. So there's a couple different ways to come at this. First thing is, for a right triangle, if this is A and this is B, what's the, in fact, not even for a right triangle. I think they give it to you. Here we go. Cool. So for any triangle, let's draw one like this, nice and freaky. And an angle in between those two sides. If I know this, side angle side, the area of the triangle is going to be 1/2 AB sine theta. And really, one way to think about this is, I know the area of a triangle is 1/2 base times height. What would this height be in terms of trig and what I know here? In terms of A and H, let's say. What would H be in terms of A? And let me kind of give it to you. Sine theta would equal what in this case, for this triangle here?
A over A.
H over A. Therefore, A sine theta is H. Cool? Multiply the sine, the A up. So in this, I could put A sine theta, and then you get that expression there. So this is the area of some triangle that's not, they don't give you the height. They just give you these sides. You kind of get the height, and they put it all together in this one equation. Now, hopefully, this will help us out here, right? They're talking about cross-sectional area. Let me see here. This is all I need from that. So what you need to find is this area, and there's which way did you try to approach this? I mean, I've kind of got, this is kind of cool here. If I draw those in, does that help at all?
No.
You're like, yay, Jeff, you just put dots up there. Thanks. Well, what have I really done here? Yeah, I've got two right triangles, and right in the middle is a beautiful shape for area.
Rectangle.
It's a rectangle. So if I could just figure out what this side is, I multiply that by that, and that's the area of the rectangle, and I find the area of the triangle, add them together. That's sort of like looking what they did here. Almost, kind of, sort of. So, in this triangle, we know, they tell me what the theta is?
No.
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 I love it. Cool. So this side is going to be how related. I know the hypotenuse. Let me pull this triangle down for us. Right. So this triangle is now here. I match it out the same. If that's theta, what's this? Theta.
So they are 90 degrees?
Yeah. The minute I drew that in, that's 90 degrees now, right? Is that cool? I didn't cheat. I'm not assuming anything. I've drawn it so it's 90 degrees. So which trig function is going to give me, now this is a little weird because my theta is up there, but I need this bottom side, don't I? That's my dotted side. So if you look at it like this, which trig function relates this to this?
No, theta is the other one.
Yeah, this will be y. Y equals, oops, sine theta equals y over 10. So y is 10 sine theta. That's looking promising, isn't it?
Which theta?
Not 10, John. Too many tens. So this now is 10 sine theta, and I'm going to stop right there because you have enough now to go forward.
Which theta?
You guys are like, no. But here's the gutter. You know this length here is 10 sine theta. And you know this is 10, this is 10, this is 10. All right, you know all this stuff here. So you can get the, what's the area of the rectangle, for example? Yeah, 10 times 10 sine theta, 100 sine. Oh. Right? Now somehow you get the area of those two triangles, and somehow it's going to come out to be this. So I need to leave you something to do. So that's what I'll leave you to do. So that was the key part of this, was figuring out that length there. Very often you want to take a problem and try to find the right triangles, especially because we haven't done 6-4 and 6-5 yet, or 6-5, 6-6, whatever. We have to deal with right triangles, right? Okay.
I don't know, can you go a little further?
Yeah, a little bit.
I don't really know what's going on.
How do I get the area of this here? So this is, here's theta, and we figured out this is theta here, right?
I guess. Because this is a.
No guessing. So let me basically get you there, because it's one step away, really. I mean, what is it about this triangle that I need to know to really get the area of it easily? Is everybody cool? We're obviously trying to get the areas of these things. I got the area of the chunk in the middle. If I just get the area of one of these triangles, the other one's the same. Symmetry here, right? So we don't have to do both. I already done one. So if I can get this area, and what is it about this triangle that's keeping me? I know this side now is 10 sine theta.
That one, 10
Here's the
cosine.
height. So if I just knew this one, I could get 1/2 the base times the height. I know the area of the triangle.
10 cosine.
Yeah, this is 10 sine theta. This must be 10 cosine theta, right? So again, so hopeful I am. So this triangle, is everybody cool with the fact that this side is 10 sine theta? Because if I say this is y, sine theta is y over 10, so y equals 10 sine theta. Now here's x. Which trig function relates this and this? Cosine. So cosine theta equals x over 10, so x is 10 cosine theta. So what's the area of the triangle then? 1/2 base times height, base times height.
Can we just not half it since there's two of them?
Yeah, good. You can say the total area would be twice that.
And then the square.
So 10 times 10 is 100, sine times cosine is sine cosine. I mean, so now the problem is done. Jeff is sad.
You go further?
All right, now, I don't want to be mean, but that's it. That's the end. I can't. We finished it. I'm not sure how to go further. That's going to freak me out. Now we'll go
That's the
further
answer.
if we fill it halfway with brain. No. Yeah, the only way to go further is to make an uglier problem. I'm not going to do that.
So that would be the answer.
That's it.
Awesome.
So when you see this problem, it almost sucks when they give you problems, especially when you get to this level, where they give you problems about show that this is the way, and you're like, how in the hell would I ever get this? And it's not obvious that this would somehow become this. So you just forget about that for a minute, and you look at the shape you're given. And areas, you almost always want to break it down into shapes you know. I found a nice rectangle. That's awesome. Rectangles are super awesome. And the minute I draw that rectangle, it tells me I have to know that side. So it's all about how to start a problem when they give it to you. If it's an area problem, one way to approach it is, how do I break this area down into shapes I know? And now that we know trig, without trig, there's no way in hell I could ever figure out how long that side is. No way in hell. But now I can. I got my nice rectangle. I've got angle, I've got length, I can figure out what that length is there. Cool? Semi-decent? So now they say, well, if we put it to an angle of 10 degrees, what area would we get? 20, is that enough area? 30, is that enough area? They have a function that'll tell them how much area they could expect. If theta is 0, what happens? What sign is 0?
0.
0. So the whole thing goes to 0. Of course, if I don't fold it up at all, how much area do I have? None. I got a freaking line. You with me? A little bit? Okay, good. So at least it makes sense there. So what? Anything else? Okay.
Well, we used that the function
Are you gonna put something like this on the test?
Could be.
Oh, wow.
That's one of my favorite questions.
A. And A for
This was in the homework. Could it be on the test? The answer to that question is always yes.
Aww.
Yeah. I could give you questions that you don't see at all in the homework. Don't want that. Yeah.
Number 54,
yeah.
on page 448.
448. Which one?
Number 54.
54.
Yeah, I was gonna say this is the question.
Oh yeah, cool.
But I don't understand.
So if you've done the homework up to this point, you will remember the flagpole problem. Maybe.
Yeah.
Yeah.
And the lady, here's my lady. She's looking at this flagpole. Look on this little hill. This is 18, 14. And we know the flagpole is 60 feet tall. And real quick word about depression and elevation. Right? This is not sound like psychology class. Depression is, it's always, both of those are related to the horizontal. So if I was telling a student, if I was in the Grand Canyon and I saw something shiny down there, it would be like at an angle of depression of 12 degrees. That's where I see it. Related to straight across, I have to look down a little bit. That's why it's called angle of depression. I depress the angle. If you're up in an airplane, you look down and you see somebody standing there, angle of depression to the person is from straight across down, what that angle is. Angle of elevation the other way around. When she looks up, that's angle of elevation. When she looks down, that's angle of depression. They were nice though, they gave you the picture. Normally the hard part about these problems is drawing the picture, but they did that for you in a lot of these. So the question is, what is this distance here? How far away is she from the flagpole? And then you say to her, just walk to the damn thing and give us a break. But we'll deal with it. Let's see, blah, blah, blah. So they basically gave you what you need here. By drawing in that dotted line, what have they created? Right triangles, thank God, because we need right triangles for any of this stuff to work so far. So what do I definitely not care about with these little right triangles? Any side of them that I don't care about at all? Yeah, I don't care about this side or that side, so don't involve those sides at all. Don't care about it. I have the side that I want to know something about, and they both share this side, right? And then I have the sides that I know something about. Not directly, because I don't know what either one is, but I know that they add to be 60. So actually, Michaela, I don't know, you were here in my office earlier, we were doing a problem that was sort of like this one, just turned around, another problem. I can't remember now how I did this one, but now I'm thinking about the way that we did the other one. So look at this right triangle here. What side of it do I want to find that's going to relate to something else I know? Yeah, this side. I like it. The Y side. We'll call it Y1. And of course, the same thing for that guy. I want to find this side, Y2. Once you get Y1 and Y2, they're not going to be numbers because they involve X. But you know what Y1 and Y2 have to do. What do they have to do? Add up to be 60. So then that's where your equation is going to come from. So I'll do another couple of steps, and then I'm going to stop no matter what you say. So Y1 is what? How do I get Y1?
60 over x. Or x over 60.
Or actually, how do I get Y1? Let me start. What trig function do I want to use? Tangent. So tangent of 18 is what over what?
Y1
Y1 over x. I like it. So that means that Y1 is x tangent 18. Cool. So Y2, incredibly enough, I can pretty much jump to it, hopefully. Y2 is going to be same thing except 14, right? Now this and this have to add to be 60. Now that's where I'll stop. That's where your equation comes in. You can solve it from there. The hard part is done.
That's the equation.
Yeah. Is that all right? Who asked the question? Does that get you going? Far enough? Yeah. Okay. Yeah.
64, that problem that we did before, it has A, B, and C. And B is graph the function A for
Oh, I'm sorry.
theta
Where were we?
is between 0 and pi over 2.
Where are we at? Sorry.
Page number is 460, sorry.
Oh yeah.
Number
So the
64.
gutter one.
The gutter one, yeah.
Ooh, cool.
So it says graph a function in my window.
Yeah.
Yeah, that's me.
So they just want you to do that in the graphic calculator.
I tried.
That's degrees.
Why? Why is it degrees
The
versus
really
Kelvin?
cool thing is, yeah, and it shouldn't be degrees necessarily.
What number?
They want you to do, this is that rain gutter one we just did.
Oh.
And part B says graph it for theta between pi over 2 and between 0 to pi over 2 in the first quadrant. So you put this in your graphing calculator. And the nice thing is, under your window, what do you want, what do you want x min and x max to be? Yeah, x min can be 0. X max can be pi divided by 2. And you can put that in there directly. I'll make this like -1 to pi over 2 plus 1 or something, just to give it a little more room, but you can do whatever you want to with that.
How about this is different?
Pi over 2 plus something.
Only a little different.
When you do that. Do you see it?
Yeah, I guess so. I just copy this down and ready for that problem.
That's all I want you to do to graph it.
Go through the steps. Picture here.
So 0 is 0 plus, for pi over 2 it should be 100, right? Pi over 2 would be 100. And then somewhere in here, I'm guessing it probably does something like this. I don't know. What's it look like?
No, it just goes in a straight line.
Straight line?
And it doesn't hit 100.
Well, it's pi over 2. What's sine of pi over 2? What's sine of pi over 2? 1. What's cosine of pi over 2? 0. So you get 100. So at pi over 2, it should be 100. Think about what that really means. If I pull in these sides that are 10, if I put them at a 90-degree angle, won't there be a 10 by 10 rectangle?
Mm-hmm.
So the area should be 100?
What am I doing wrong?
I don't know. So could you see me after class? So the rest of you guys,
I don't get it.
you put this in your calculator. I can't remember now if sine opens up so it's going to be sine x, right? When you put it in your calculator, sine x, cosine x. Make sure it's in radians. Make sure your mode is radians.
Oh, it's different.
All right. So does it look more like what I thought it might?
Maybe.
Maybe.
I'll see what it
Okay. Anything else from homework? Okay. So I kind of gave us a little bit of an intro to these last couple sections in 6. 6 takes this and makes it better. Right? And I kind of like this from your perspective, because a lot of you guys just know a squared plus b squared c squared so much, you're like, I didn't know you could mess with that at all. But it only works for right triangles. There must be something I could do to make it work for any freaking triangle. And there is. There's a little adjustment we can make. The adjustment's going to be a little bit ugly, but oh well. In 6.5, we're going to talk about right now. I want to first show you why it works. Let me think about why I want to do that. No, I want to first talk to you why we might want to do something like this. So if you remember from geometry, angle, side angle, right? Or side angle, angle. Or one of my favorite ones, SSA, which of course when I was in 11th grade we would turn it around. But what do these really mean? I like to think of them as somebody giving me parts to put together a triangle. That's really what it is. If somebody gives me a side and 2 angles, angle A and angle B, then that defines a triangle, if you think about it. Because you can't, if you put this side too long, then that side's gonna, there's only one way it could be then. So in black are the parts they would give me, angle, side, angle. And actually, it's kind of nice, the way that they put this together, the side's got to be in the middle of the two angles, like that. How are we doing so far? Now the funny thing is, if you think about it, do I only know two angles in there? No. I know all three now because they have to add up to be 180, so I really know the third one too. Okay, how are we doing so far? So they give me a side and then two angles that my other sides have to be at. That defines a triangle. There's only one triangle that could do that. How are we doing so far? Okay. And then side. Oh yeah, side angle is really the same thing because, like I said, we have that last angle no matter what we do. How are we doing so far? Okay, cool. So those are both kind of represented here. Side angle is the one that's a little more complicated. Doesn't sound too bad. So somebody gives me a side, and they give me another side, and they give me an angle that I need to use. And so this angle is not between these two sides, or else it would have been in the middle. It would have been SAS. You guys kind of with me? So it's got to be side, and then some angle coming off here. So this bottom side, so this is going to connect onto this side somehow. It could be in any orientation. I really want you guys with me to see why this is a little bit freaky. The bottom then could be any length it needs to be. Do I specify how long that last side is? No. So it can be as long as you need. So if I take this thing in here, and I was trying to experiment with a few things I could do. See if this will work. I could fit that last side, say my marker is that last side. I could fit it in like this, or I could fit it in like this and make some really funky little triangle like that. So in the book, it's a little bit better because you can see the swinging that it does. If you look on page 471, it's a little hard to do this up here on the board, but page 471, you have this side set. You have this angle set. And then this last side, you can come in like this, or it could swing over to here. So I could have this triangle, or I could have that bigger triangle. Are you guys with me? Now, on one level, I want you to understand why that happens conceptually. Then you got to see what to be careful about when you're doing these problems. At some point in the problem, you're going to get an angle that you got to go, oh crap, it could be the other situation. So you got to give me both answers, and that's one of the easiest things in the world to miss. So I'll tell you what, to get us into this, we'll do some of these first, and then we'll attack some of those, because those get freaky. So what the hell is this law of sines then? This is what it works with. These triangles that I described here, that's what it works with. How does it work? And one thing I want to say, this is true for all triangles, not just right triangles. That's why it's a useful law to know. It's better than Pythagorean. So one way to kind of show this, and I think the way I'm going to stick with because it's the quickest way to show it, just be up front. This works for any triangle. It's just easiest to see this with an equilateral or isosceles, whatever the hell you want to call this thing. So let me set up, here's angle A, angle B, angle C. And the reason we're sort of going away from theta is, number one, I've got three angles now. I don't want to use theta 1, theta 2, theta 3. Plus, it makes it easier because now I have three sides. So of course I'm going to call this side little a because it's across from big A. You stop right there. You guys cool with that? So it makes it easier to tell what goes with what. And why does this make intuitive sense? Because if I open B bigger, little b gets larger. So they directly affect each other. So they go, oh. So let me draw in one little thing here. So I've just made two right triangles there, right? Even if it's not equilateral, it's still going to make two right triangles. Can somebody give me one representation for H using some trig functions?
Sine, A sine C.
Sine.
All right, so sine of what?
C. A sine C.
Sine of A, okay. So sine of A would equal what over what?
H over C.
H over C. So H equals C sine A. Is that cool? How are we doing so far? Is that all right? Nothing major there. It's the y piece over that hypotenuse. Ooh. And what's sine of C? Sine of C would be H over A. So H equals A sine C. Is that cool? So far, so good? All right. So now what must be true about these two things? They must be equal to each other. So C sine A must equal A sine C. And if I write this a little bit better, sine A over little a equals sine C over little c. So what you probably expect will happen, what one piece am I missing from this? Probably sine B over little b. And it's true. So let's work that in there. One last little. Is everybody semi with me so far? I mean, I haven't done anything amazing. Right? You never do, Jeff. That's all right. So I drew the H in, making right triangles. I can describe H in two different ways, which means those two ways must equal each other. Now, let's see what the best way to do this, because I don't have that many colors to work with. If I drew another H in here, let me draw it again. That might be better. Okay, cool. How are we doing? So if I drew a height this way instead, we'll call this H1. So everything's kind of turned around at all. Then H1, what would sine of B be? Sine of B would be H over C. H1, sorry. You can do it, Jeff. H1 over C. So H1 equals C sine B. Is that cool? Okay, so far so good. And what's another way to do H1? Same idea. So now sine of C would be H1 over B. So I got B sine C. Now this is a totally different height, right? Possibly, if I have a triangle that's not equilateral, that would be a different height. But what really matters is from this I get something that's true in general, because the heights go away. So I get the same thing, don't I? I get sine B over B equals sine C over C. Well, what do I know about sine C over C? Equals sine A over A. So now I get a complete little statement. It's the first time and one of the few times you have seen and are allowed to have more than one equal sign in a row. Right? Now that, I don't know if you are worried about how that's going to work. Law of sines kicks so much ass. It is so nice. Trust me. And if I'm you, I might be worried. I'm like, oh shit, law of cosines must be ugly as hell. It's a little worse, but it's not horrible. So let's try a problem out. I'm going to take it right out of the book here. Yeah. So I want you to realize something. We haven't talked about law of cosines yet, but do you notice how law of sines can only work if you're given a triangle that has a side and its related angle? If I don't have that, how the hell can I ever use these ratios? Let me say that again. This problem here, it has this angle. Does it have its associated side? Yes. So what ratio can I set up then from the C's? Sine of 25 over
80.4.
80.4 sine of 20. What's this little side here? This is going to be A there, right? Because this is across from angle A. You guys with me here? So if I have an angle and its side across from it, that's a ratio I can set up. And then I can equal it to some other ratio, and the other ratio is going to have something I don't know, so I can solve for it. So here I know 20, but I don't have a clue what A is. So now I can solve for it. Yes?
I'm hung up on, I don't understand why sine of big A is over little a. That just seems like, ooh, I don't understand why.
Are you okay with these?
Yes.
Cool. If you're okay with these, that means that this must equal this.
Yeah.
Then I divide by C and I divide by A and I get this.
Okay. Sure.
So if you're cool with this is inescapable,
Yeah. Okay, now I get it.
which is a word I always try to use. Simple.
Inescapable?
Yes, that's inescapable. Cool. And we went further and we had to bring in another height, but I finished the connection between all three. Okay, cool. So that means any ratio that you can make, you can make it and then set it equal to any other ratio that you need to know something about.
This bottom part though, the BCA all equal to each other, that's only if it's an equilateral, isn't it?
No. I could have done other triangles and it would have worked the same way. It just would have taken a little more work to do a triangle like this. Then the height would have been external, but it would have still worked out the same way. I would have called this H. I could have done it two different ways. But just to make it a little easier to get into, I wanted to use a nice triangle that's easy to draw. It would have worked exactly the same way with this one. It's just a harder visual because my height's outside of the triangle.
What about this one?
Is that cool so far? Just the. So I like the fact that you're calling me out on using an easy triangle, but I did that mostly just because it's visually easy to see. It would have worked the same way with this. Cool. Maybe. There's actually a whole other. Using this triangle real quick. I'll show you this. So let's say, remember the area of this is going to be 1/2 AB sine C in this case. It's always the included angle. So the area, this is 1/2 AB sine C. What's another way to say the area? 1/2 BC sine A. It's always got to be the included angle. Does that make sense what I mean by included? What's included with B and C? A. What's included with A and B? C. So BC would be sine A. And another way to do the area would be 1/2 AC sine B. So now if you set that equal to that, the B's will go away, you end up with A sine C equals C sine A, which is where we got over there. If you set that equal to that, you'll end up with B and A doing it, and then you get the whole thing. Are you guys with me? Yeah.
This is law of Gossard, right?
This is law of sines.
No,
No, this is law of sines.
Still?
Yeah. Again, if I set these equal to each other, like this guy to that, why can I set them equal to each other? Because they all represent the area of that same triangle, right? What happens? The 1/2s go away, the C's go away. I get B sine A equals A sine B, which is the same thing I had. Do they have it? No, that's the one I didn't get over there, of course. Sine A over A equals sine B over B. And then I can do the same thing with these two and complete that line. So it's a whole other way to prove this. I kind of like this way better, but this is fine too. They're the same. But it's easier for different uglier triangles to do it this way. Yeah. All right, so how do I solve this for A?
Hold on. What did you get for height?
So sine 20 over sine 25 times 80.4. Is that cool? Cross multiply, whatever you want to do. You're going to get there.
All we did was use half the image.
So this is now a general rule. This is true for any given triangle, that is true. Period. So when I have a triangle that I don't know parts of it, I could set up these ratios. So I see a side and its angle. So that sets up the fully known thing. And then I see an angle and I don't know the other side. That sets up the part that has an unknown in it. Now I can solve for that unknown. And what do you guys get for this? Can somebody?
65.07 something.
65.07? I don't know. Does that picture look right?
Should be, yes.
It's gruesome. Yeah, my picture's a little off. That side's not really that small, but it should certainly be smaller than this. Does that make sense?
Yeah.
Because that opened up 25, this only opens up 20. So it makes sense that it's smaller.
How come we got a negative number?
Radians or degrees?
Radians.
Ah.
I use this little change in the calculator from 1 to
And how do I get these last couple things? How do I get angle B? Magic?
180 minus.
Yeah, 180 minus 45. 135. And now I can set up that last ratio, right?
I need it. I need it.
And I'll tell you this, the ratio I'm going to use is the one that's the stuff that they gave me. Because if I made a mistake here, I don't want to use that ratio and just make another mistake on top of that. I don't know if you guys really understand. I'm going to use that ratio again. Because that's the ratio that they gave me. So I know that one's right. I might have made a mistake here. I'm not going to use that unless I have to. Just in case. So sine 25 over 80.4 equals sine of what?
135.
135 over B. And they can solve for B.
And big B always angles?
Yeah, big letters always angles. Small letters always sines. Cool. Yeah.
For A, can it also be 80.4 sine of 20 over sine of 25? Same thing?
Yeah, it's the same thing. Yeah. Same thing. How are we feeling so far? I mean, the initial thing is a little the initial thing is a little hard to get into the concept of it. But if I'm you, I'm loving the fact that this is just setting up ratios, and I mean, I can really sink my teeth into this. Right? It's a little less vague than some of the stuff we were just doing. So let me give you one, and I'm gonna not say a word. You guys do this. All right. By the way, which case is this? What's the three letters I can use? The S's and the A's. Angle, side angle. Just a new wire. All right, so go ahead. So when they say solve the triangle, that sounds strange. What they mean is get everything about it known. All three angles, all three sides. So go for it. Help you out a little bit. make me feel a little better, make sure everybody's on the right track. What's the first thing you have to figure out?
The last angle
Yeah.
of sine 2.
Otherwise, you can't set up any ratios, right? Any known ratios.
Oh, radians or degrees? Or is it
Degrees.
degrees?
Yeah, it tells you.
You're too excited with your answer. Go ahead.
For what?
Seems like you're getting stressed.
I'm fine. All right. So what ratio can I set up? So that's the one that I know everything about. And then I can really just pick. So I can set up like sine of 100 over C. So C is twice sine of 100 over sine 50. And then whatever the hell that is. 2.57? So that's C. C is 2.57. And the only thing I don't know still is A, little a. So I do the same thing again. Sine 50 over 2. Yeah.
Why? How come on that one you did the whole thing multiplied by 80.40 and then that one you just multiplied by 10?
Okay. If I give you this equation, can you solve it? Good. That's all. So I happen to multiply the 2 up. It doesn't matter how I write this. Now,
I got 3.8.
at one level, you have to use your algebra. So how could I write this? I could write like that. I could write it like this. If I felt like it. They all mean the same thing.
Alright.
Okay, good. So I want us to focus on what is truly pre-calc concept, not how I chose to write what I'm doing. Don't worry about that. So this one I can set up sine 30 over A. This has got the extra added bonus. I know what sine 30 is, but it doesn't really matter. You just put it all in the calculator. So twice sine 30 over sine 50. So whatever that is.
1.31.
1.31? So when I ask you, if I ask you in a quiz or a test to solve the triangle, you know you're done when you get all 3 angles, all 3 sides. Cool. So do you want to take a break or do you want to keep going? Because I tell you what, my plan today is to finish out 6 and just do a little intro to 7 and then head out. That's the plan. We got 50-50 on this. So how about we take a 10-minute break? Is that all right?
Yep. Perfect.
All right, we'll take a 10-minute break. Come back 22 after.